Okay, the probability worksheet. The first thing we've got here is a survey. 50 students were asked when their birthday is, and those have gone in categories January to March, April to June, July to September, October to December. Now the relative frequency is like an experimental probability. Out of those 50 students, how many had a birthday in April, May, or June? So, April, May, and June, that's this category over here. So it's simply 21 in that category, that's the frequency, out of 50 related to the 50. So 21 out of 50, that's our final answer. If you type that into your calculator, you'll see if the fraction simplifies. It doesn't. You can write it as a decimal if you really want to, 0.42, but I'm going to stick to fractions because it's less work. In part B, there are 750 students in the school. I want to estimate the number of students who have a birthday in April, May, or June. So the way we do estimates with probabilities or relative frequencies is to take that probability or that relative frequency and multiply it by the number of things we're interested in. Remember that a probability says I would expect, say in this case, 21/50ths of the time to find a student with that birthday. 21/50ths of 750 times in this case. Remember in maths, the word of means multiply, and that's why I'm timesing them together. So I'm going to take that, multiply by 750, and I'm going to get an answer of 315 students estimated to have a birthday in those months. Question 2. The probability that Stephanie wins her next tennis match is 0.85. The probability she does not win her next tennis match has to be whatever makes it up to 1. Remember, the probability of something not happening is equal to 1 minus the probability that it does happen. So in this case, it's 1 minus 0.85, which is 0.15, and that's our final answer. In a large box, 13 of the 52 biscuits are chocolate, and Leo takes a biscuit from the box at random. I want to find the probability that his biscuit is a chocolate biscuit. Well, 13 out of those 52 are chocolate. Type that into your calculator, and it will give you a fraction simplified down to 1/4. So that's the probability of a chocolate biscuit, and now I want the probability the biscuit is not chocolate. Remember, this has got to be 1 minus 1/4, which is 3/4. This is 0 over here, this is 1. That's a half, so this over here will be the 3/4. So that's where I would draw my arrow, at 3/4. A bag contains 16 counters. 3 are red, 6 are blue, and the rest are yellow. We're taking a counter from the bag at random, and I want to know which one's most likely. Well, 3 are red and 6 are blue. That's 9 altogether, so the rest are yellow. Well, that's 7 of them. So altogether, the most likely one is the yellow one because there's more of them. So yellow is the colour he's most likely to take. The probability of a red counter is 3 out of 16. So that's all I need to do there. I don't need to write down the decimal. Leaving it as a fraction is absolutely fine. And check it simplifies on your calculator if you're not sure. In a survey of 40 workers, 6 cycle to the office. There's 800 workers, and I want to know how many cycle to the office, an estimate of it. Well, first of all, I need a probability, or a relative frequency, in this case. 6 out of 40 is my relative frequency, my probability of finding someone who cycles to the office. 6/40ths of the time, of the 800 times I ask people, I'm going to find a cyclist. So there's my calculation. 6/40ths times 800. And that's getting me 120. Probability times the number of people you're asking or the number of times you're looking. That's how we do estimates and expected values. A bag contains 20 counters, 6 are red, 9 are blue, and the rest are white. The rest are white is not very useful to us, so once again I'm going to work that out. 6 and 9 make 15, so there are 5 white counters. Jared takes one counter at random. The chances of getting a red counter are 6 out of 20. A white counter, 5 out of 20. A yellow counter, well, there aren't any yellow counters, it's 0. I would also want to make sure I wrote these fractions in their simplest terms. So 6/20ths would actually be 3/10, 5/20ths would be 1/4. A bag contains green counters, black counters, purple counters, and brown counters, and I want to complete the table. Now all probabilities must add up to 1. If we add all of these together, we must always get 1. So the missing one over here is what I get when I subtract all this stuff from 1. Let's add up 0.3, 0.24, and 0.18. 0.3 add 0.24 add 0.18 all comes out as 0.72. 1 minus 0.72 is equal to 0.28. So that must be what goes in here, the probability of a green counter. Bag C contains 8 red counters and 12 blue counters only. Bag D contains 6 reds and 9 blues. A counter is taken at random from each bag. We want the probability of taking a red counter from bag C equal to the probability of taking a red counter from bag D. So let's work out the probability from C. From bag C, the probability of getting a red counter is 8 red counters out of, there are 20 altogether. Let's write this as a decimal because it's going to be easier to compare things if they're written as decimals. 8/20ths goes down to 0.4 as a decimal. Going from bag D, there are 6 red counters in bag D out of a total of 15 altogether. If you type this into your calculator, 6 out of 15, and convert that to a decimal, you get the same answer. So the probabilities are the same. So we're doing a very sort of standard job here, but it's being expressed in a different way. Don't freak out. The table shows the results of a survey in a village. It shows the number of males and females who are left-handed, right-handed, or ambidextrous, and I want to complete the table. So we've got a missing quantity over here. Now we can look across the row or down the column. If we look down the column, for instance, the total for this column is 164. With 102 sitting over here, we need to figure out what's missing, and it is of course 62 missing to make the total up to 164. Now if we check along the row, we can just confirm that. 17 plus 62 is 79, add 5 is 84, so I'm happy with that result. Now, I want to write down the probability that a male chosen at random is left-handed. Well, there are 17 left-handed males, and I'm choosing from 210. So that's my probability. 17 divided by 210 doesn't simplify, so I'm going to leave that as it is. A left-handed, now watch very carefully, this is the trickiest question we've seen so far. Read this very, very carefully. A left-handed person is chosen, and I want to know the probability they're female. Well, if we're just choosing left-handed people, I'm choosing out of a total of 38. And out of those 38 people, 21 are left-handed. So be very, very careful reading the wording of these questions. A person chosen, in fact, I just made a mistake. Here's a teaching moment. I didn't follow my own instructions, I rushed through. A male chosen at random is left-handed. That result was wrong. I should have been choosing just from the males. I should have been choosing out of 84. And I need a left-handed person out of the males. There's 17 of them. So there you go. We're not immune to mistakes even after lots of practice. Read the questions super carefully. Once again, let me just explain what happened there. I'm choosing just from the males, and there's only 84 of them. They need to be left-handed, so that's 17 out of the 84. In part C, a person chosen at random is right-handed. Now I get to choose out of the 210. And out of those 210 people, the right-handed ones are 164. On to the next question now. Bastian has a bag containing 4 types of sweet. I want to complete the table with all the probabilities. Now, once again, these all add up to 1. So I've got 0.5 plus 0.15, 0.65 altogether. From 1, that leaves 0.35 in here. And that's it. That's that question. Mrs. Jones travels on the bus to Wegmouth. The probability that she stands on the bus is 0.4. Write down the probability she does not stand on the bus. Or remember, the not is 1 minus our probability, that's 0.6. Mrs. Jones travels on the bus 85 times. We want to know the expected or estimated number of times that she stands. The probability she stands is 0.4. Think of this maybe as 40%, for instance. She stands 40% of the time. Remember, of means multiply. And the time is the 85 times she travels by bus. 40% of the 85 times. So 0.4 times 85. We would expect her to stand 34 times. Final question now. Josie wants to test if a coin is biased. She flips the coin 30 times, and here are her results. I need to complete the relative frequency table, essentially just counting how many heads and tails go in each of these boxes. So I'm going to do that right now. Okay, so I counted all those up and filled out my table with 22 heads and 8 tails. Do we think the coin is biased? Well, yes, I think I do. Okay. A fair coin would be closer to 50-50, would be closer to 15 heads and 15 tails. It wouldn't be exact, that's quite unlikely in fact that we'd get a perfect balance, but we certainly would expect to be closer to 15 and 15. Josie decides to flip the coin 150 times, and I want to estimate the number of times it will land on tails. Well, based on her results, the relative frequency, which is kind of like a probability, of tails is 8 out of 30, 8/30ths. 8/30ths of the time we'd expect tails. So 8/30ths times the 150 times would give us our result. So I'm going to do that on my calculator, and we're ending up with 40 times. We'd expect tails 40 times out of the 150. And that's it. That's all the answers on the probability worksheet.